Hello and welcome to another week, albeit a short week, of ECE 108. So this week we're going to introduce the idea of sets. We're going to talk about some special sets that I've already used and you probably already know, some classical paradoxes, the idea of subsets, set equality, Venn diagrams, set operations, and throughout this week we're going to use some of the proof techniques that we introduced in the previous week. So let's jump right on in. So what is a set? We're going to define a set to be an unordered collection of distinct objects. So there's two main ideas here, unordered and distinct. So now each of these objects in the set we're going to refer to as a member or an element of the set. Now let's give some notation for sets. So to define a set containing the elements S1 and S2, I write curly bracket S1, comma S2. So now let's go through some examples. The following are sets. So the collection ABC is a set. The collection CBA is a set. Notice that this first set and the second set, the only difference is the order of the elements in the collection. Next, the set containing 1 and the set containing 2, 3 is a set. And finally, the set of cats and lawyers is a set because cats are distinct from lawyers. Now, notice here that I can have a set of sets. At the end of this lecture, I'll talk a bit about why you need to be careful when dealing with sets of sets, but it is possible to do this. So finally, you might ask, why do the members of the set have to be distinct objects? Why can't I include the same object more than once? Well, you can, and that's referred to as a multi-set. So multi-sets will come in handy later on in the course when we talk about, say, the number of ways that you can write a word using some collection of letters. In English, we commonly use the same letter more than once in a word, so you need a multi-set to handle those type of situations. But when dealing with sets, do make sure that the collection that you're building is a collection of distinct objects. I'll probably put a question somewhere at one point, either on the assignment or more realistically, the midterm or the final, where I use this distinction between a set and a multi-set. So don't forget that sets have to be collections of distinct objects. Okay, now let's talk about a bit more notation. So if little s is an element of some set capital S, I can write little s is in S using this notation here. And if little s is not an element of the set capital S, I can write little s is not in capital S via that notation. And finally, when an element is in a set, we say that the set contains that element. So let's see a quick example of this notation. If S is this set containing S1 and S2, then I can say that S1 is in S. I can say that S3 is not in S. So in words, this is explicitly saying that the set S1 contains the element S1, but not the element S3. And note that this is little s1 and this is capital S1. You have to be careful with sets containing themselves. We'll talk about that at the end of this lecture. Now for another example, if S is the set containing 1 and the set 1 and 3, then the elements of S are, so pause the video for a second and think about what the elements should be. Well, the elements will simply be 1 and the set containing 1 and 3. So notice here that explicitly 3 is not an element of S because 3 is not in S, right? It's the set 1, 3. So this is a distinction that you need to be careful with. Now, there is a nice connection between sets and logic. In particular, if I look at the statement, little s is not in the set capital S, this can be written logically via this expression here. So explicitly, the statement that x is not an element of S is logically equivalent to saying not x is an element of S. So this connection between sets and logic can, one, give you a lot of intuition about various statements of sets, given your intuition about logic, and two, can allow you to prove things about sets a little bit quicker than if you were to try to prove it using the definition of sets and their properties. So just keep in mind that logic can sometimes be used to help prove a statement about sets. So now that we've talked about sets, a natural question to ask is, can we talk about two sets being equal? Previously, I had those two sets where I just changed the order of the elements. Would those be equal? Well, it's natural to want those sets to be equal, so let's define equality. Two sets A and B are equal, denoted by A is equal to B, if they contain the exact same elements. So this naturally gives another definition. If two sets A and B do not contain the exact same elements, well, then we're going to say that they're not equal, and we're going to write that A is not equal to B. So now let's go through some examples. So S is equal to S for all sets S. Well, that's going to be true pretty trivially. Further, the set CAB is equal to the set ABC because all I did was rearrange the order of the elements. But the set 1, 2, 3 is not equal to the set containing 1, 2, 3, and 4 because the set on the right-hand side contains 4, but the set on the left-hand side does not. And then another example, the set containing the set of 1, the set of 2, and the set of 3 is not equal to the set containing the elements 1, 2, and 3. This is simply because 1 is not the set of 1. Those are two distinct objects. So now let's introduce some special sets and some notation that you can use. So the following are special sets. N, which will be the set containing 1, 2, 3, that will be the natural numbers. W, which will be the set containing 0, 1, 2, 3, out to infinity, will be the set of whole numbers. Z will just simply be the set of integers, so positive and negative whole numbers. Q will simply be the set of all rational numbers. So here, notice that I'm not explicitly writing Q out as a collection of elements. We will do this shortly once we develop set builder notation, but for now, just Q is the set of all fractions. R is the set of all real numbers. Now, R plus will simply be the positive real numbers. R plus 0 will be the non-negative real numbers. So R plus doesn't contain 0 because 0 is neither positive nor negative, but R plus with the 0 underneath it will contain 0. So it's all the real numbers greater than or equal to 0. So R minus will be all the non-negative numbers, so all the numbers less than 0. And R minus with a 0 will be the non-positive numbers, so all numbers less than or equal to 0. So now you can mix and match up this notation. I could talk about, say, Q plus to be the set of all positive rational numbers, or say Q minus 0, so the set of all non-positive rational numbers. And there are other notations that you can use. For instance, in one of the tutorials, they introduced this notation here, and this would simply be the set of all the real numbers that are greater than or equal to A, where A is just some real number that you picked. So feel free to use any of these notations. If you have a different notation that you're wondering if you can use, ask either in office hours or better yet on Piazza so everyone can see the notation that you propose using. So now there's one more super special set. So definition, the set of no elements is called the empty set or the null set and is denoted by either this symbol here or simply two brackets with nothing in the middle. So in many applications and in many real-world problems, the null set is needed to be able to actually work with sets. So in some sense, the null set kind of acts like 0. It's not, but it's in some ways serves the same purpose. Okay, so let's introduce set builder notation. So the notation curly bracket x in U line p of x denotes the set containing all of the objects x such that 1, x is an element of U, and 2, p of x is a true statement. So here you can read this out in words saying that this is the collection of all elements x and U such that p of x is true. So this notation allows me to build new sets given some previously defined set and some proposition. So let's go through an example. So I could say let A be equal to this set. So what is this saying? Well, this is saying that A is the collection of all elements in the integers, so it's the collection of all integers, such that there exists some other integer k where n is equal to 2k. So pause the video for a second and think about what this set would actually be. Okay, so kind of unpacking this definition, this is the set of integers such that the integer is equal to 2 times another integer. Well, that's simply the set of even integers. So instead of writing A is equal to, say, -4, -2, 0, 2, 4, ... like this, I can instead simply use this nice shorter notation here. So by using this notation, I'm dramatically expanding the types of sets I can consider because there's infinitely many sets that you can't write out in a nice way. The real numbers are an example of that type of a set. Now let's introduce another notation. The notation f of x such that x is in U denotes the set of all objects of the form f of x such that x is an element of the set U. So this is slightly different than the upper notation. In practice, pretty much every set that you'll see, you can write using either notation, but let's demonstrate how to use this notation. So if we consider the set A, which will be equal to the set of elements of the form 2k for k is an integer, what is this set? Well, this set is simply the set of all even numbers. So again, both of these notations are completely valid to use. In some cases, the top notation makes things a little bit cleaner. In other cases, the bottom notation makes things cleaner. So say, for instance, if we were talking about the set of all even numbers, you would probably prefer this notation here compared to the top notation, but for other cases, you might prefer the top notation. Now let's introduce one more different type of set builder notation. So the notations of this form, or equivalently of this form where I just swap the set and the proposition, both describe the set containing all objects of the form f of x such that two things are true. One, x will be an element of u, and two, p of x is a true statement. So personally, I would prefer you to use this notation over the other form, but it doesn't technically matter which one you use. So notice that this notation is different than the notation that we introduced before. Previously, the stuff that went to the right-hand side of the bar had to be a true statement, and now using this notation, we have a bit more leniency with what we can do on the right-hand side of this bar. So let's give an example of the type of set that we can define via this notation. Q is simply the set of all elements of the form a divided by b, such that a and b are integers, and the proposition would be that b is not equal to 0, and a and b have no common factors other than 1. One thing before we go on to the next slide, notice here that this statement a and b have no common factors other than 1 is required to make Q a set. Explicitly, without this second comment here, I could have an element say 1/2 and an element say 2/4, and we all know that 1/2 is equal to 2/4. So without this statement here, we're including elements multiple times. It is worth noting that in many contexts, explicitly in contexts where you're not dealing with multi-sets, you can get rid of this extra statement here and simply collapse all the elements onto each other. For instance, you could say that the set containing 1, 1, 1, 1, 1, 1, 1, and only those elements would simply be the set containing 1, since the original set simply contained 1 multiple times. And this convention can make things a little bit easier, but since in this course we're going to be using multi-sets later on, you will need to be explicit in ensuring that your set does not contain the same element multiple times. So just a fair warning, tying back into the multi-set versus set comment, there will probably be questions on either the midterm or the final regarding whether or not something is a set, and I might give you something that it is a multi-set but is not a set, so make sure that you understand this distinction. Now let's give some more examples of set builder notation. Use set builder notation to write the set of all multiples of 7. So pause the video and try this example on your own before I give you the solution. Okay, so how could we write this? Well, we could say this is the set of all integers, so the set of all n and z, such that 7 divides n. So that's one way of writing it. It's a bit cumbersome. It's not really the best way to write this set, so let's think of another way. Well, we could also write this as the set of all 7 times k, where k is an integer. Okay, good. Let's look at one more example. The set of all odd perfect squares. So recall that a perfect square is a number that can be written as the square of some integer. Now take a bit of time and try to write this out using set notation on your own before I give you the solution. Okay, so how could I write this? Well, there's two things I need. I need the number to be odd, and I need the number to be a perfect square. So there's multiple ways that I can handle this. One way to write this would be to use brute force. So the collection of all n and n. So here I'm restricting myself to n instead of z because perfect squares will always be positive. And this simply comes from the fact that the square of any integer is always positive. This said, it's not incorrect to write z here, given that the restrictions that you impose on n are such that it has to be positive. Okay, so the set of all natural numbers such that what? Well, in order for it to be a perfect square, there has to exist a k and z such that n is equal to k squared. So that covers the perfect square bit. And for n to be odd, what do I need? Well, there has to exist an I and z such that n is equal to 2k plus 1. So now regarding my comments about using z instead of n here, this statement here that there exists a k and z such that n is equal to k squared, that imposes that n has to be positive. So from there I can freely swap this n with a z if I wanted. It's just a bit more accurate or a bit more terse to say that n is an element of the natural numbers rather than the integers. Okay, so this is one way of writing this. This is kind of cumbersome, it's kind of long. Can we think of a way to write this in a more compact form? So explicitly, can I get rid of one of these statements over here by modifying this n as an element of n? So take a little bit of time and try doing that on your own. Okay, so what's another way that I could write this? Well, I could simply say that this is the set of all k squared, so elements of the form k squared, where k is an integer, and 2 does not divide k squared. So what is this notation saying? Well, since the elements of this set are of the form k squared, I know the elements of this set are going to be perfect squares given that k is an integer. So on the right-hand side, I have that k is an integer, therefore I'm good for perfect square. In terms of odd, well, how do I handle the odd part? Well, I know that a number is odd if and only if it's not even. So from there, I know that a number is odd if and only if it's not divisible by 2. So this is another way of writing this set of all odd perfect squares. Now, we can go one step even further for this problem. So pause the video for a second and see if you can think of a way to include this set here to the left-hand side. Okay, well, I know if 2 doesn't divide k squared, then I know this k squared has to be of the form 2n plus 1. So what I can do is I can simply plug this 2i plus 1 into this k squared, expand it out, and lo and behold, I get this set. So this is the set of all elements of the form 4k squared plus 4k plus 1, such that k is an integer. So again, here all I did was take 2k plus 1 quantity, square that, expand it out to get this form. So here you can see there's lots of different ways to write sets. None of these ways of writing this set are particularly more accurate than any of the others. But if I wanted to prove something about the odd perfect squares, being able to start with something of this form is a bit nicer than being able to start with something of this kind of more complex form. So do keep this in mind when working with sets. It is sometimes easier to use a different definition for your set. Okay, one more example. All points on a circle of radius 8 centered at the origin. Now, before telling you to go off and try to write this set on your own, let's think about what this set is a little bit. The elements of this set are going to be points. In particular, they're going to be points on a circle of radius 8 centered at the origin. So the elements of this set are going to be things of the form a comma b, where a and b are real numbers, and these points have the property that they lie on this circle of radius 8 centered at the origin. So now take a little bit of time and think of how you could write this set out. Okay, so there's multiple ways of writing this. So I could say this is the collection of all points of the form x and y, such that x and y are real numbers, and x squared plus y squared is equal to 8 squared. So here I'm just simply saying that these are points here that satisfy the property that they lie on this curve that represents a circle of radius 8 centered at the origin. Another way that I could write this out would simply be the set of all points of the form 8 sine of theta, comma 8 cos of theta, where theta is a real number. So here, if I plug this 8 sine theta, 8 cos theta in for x and y into this equation, I get that the equality holds. Therefore, I can simplify the above set into this bottom set here. Okay, so if you have any other questions on set builder notation, ask in office hours or Piazza. I've kind of covered the majority of the different ways you might want to use set builder notation between all of the examples that I've discussed, but your use of set builder notation strongly depends on the particular set that you're writing. So if you do find a set that you're unsure of how to write in set builder notation, just ask me. So now let's talk about the set complement and the universal sets. For any given set S, the set of all of the elements that are not in S, denoted by S bar, is called the complement of S. So previously, I talked about elements being in a set S, which naturally let me talk about elements not being in a set S. So now this idea introduces the concept of talking of all of the elements that are not in the set S. Well, this begs several questions, and kind of a natural way of jumping into those questions is to ask this question here. what is the complement of the null set? Well, the null set contains nothing, right? And what is the opposite of nothing? Well, everything. So the complement of the null set is the set of everything. So what is the set of everything? Well, it turns out that in naive set theory, which is the set theory that we're introducing here, this concept of everything is a pretty dangerous concept. And it took Hilbert and a lot of really smart mathematicians to kind of quantify what everything is. And the last 2 slides of this lecture will talk about some of the arguments of why the set of everything isn't really defined or formally doesn't exist within naive set theory. So enough abstraction for now. We will define the universal set, or the universe, denoted by this fancy U, to be the complement of the null set. So again, this doesn't really fix this problem of what everything is. I'm just defining it to be this new set U. So what is U? Well, U will depend on what you are talking about. So depending on the context of a given problem, we're going to pick a universal set to work with. There is no global universal set that works in all cases. So now in particular, depending on the context, I will often pick the universal set to be the domain of discourse. So what is the domain of discourse? Well, the domain of discourse is the domain that I'm kind of talking about for that problem or for, say, that paper or that book or whatever. So let's give some examples. If I'm working with the real numbers, I would pick the domain of discourse to be the real numbers. So explicitly, I would say that the universe is equal to R, and thus the complement of the set containing 1, 2, 3 would simply be the set of all real numbers such that x is not equal to 1 or 2 or 3. Okay, on the other hand, if I was talking about divisibility, we typically talk about divisibility in the context of the integers. Therefore, I would say that U is equal to the set of all integers, and thus the complement of the set 1, 2, 3 would simply be the set of all integers such that n is greater than or equal to 4 or n is less than 0. So now, generally, if I don't explicitly state what the universe is, you kind of have to think from the context of the problem, what set am I realistically working in? So now, again, why don't I let the universal set simply be equal to the set of all sets? So we know sets can contain other sets, right? So if I consider the set of all sets, that should surely contain absolutely anything you will ever want to talk about ever. Well, it turns out that in naive set theory, this is a fundamental problem. So now, to understand why the set of all sets is not something that you can really consider, let's look at a paradox. So, the Barber Paradox. Again, why not just pick the universal set to be the set of all sets? Well, we're going to look at a classical analogy first, and then I'm going to introduce Russell's paradox. So, consider a town where everyone shaves. No matter what their gender is, they shave. This town has a barber, who is also a cat, who follows one simple rule. The rule is P, the barber shaves all those and only those who do not shave themselves. So here I'm using P to refer to this statement here. Okay, let's ask a simple question. Who shaves the barber? So if you like brain teasers or those type things, pause the video now and go through the 2 cases to try to figure out who shaves the barber. Okay, now let's examine 2 cases. Suppose the barber shaves themselves. Well, since P, as a rule, is always true, since the barber shaves themselves, they cannot shave themselves, right? Because the barber shaves those and only those who do not shave themselves. And since the barber shaves himself, he can't. So in this case, the barber can't shave himself because P is true. Now this is a contradiction, therefore this case can't be true. So the barber cannot shave himself. Okay, that's nice. Now let's examine the case where the barber does not shave theirself. Now in this town, everyone shaves, therefore someone must shave the barber. But since the barber doesn't shave themselves, then the barber has to shave himself because the barber shaves all of those who do not shave themselves. Thus, in this case, the barber must shave himself as well. This is, again, another contradiction. So putting all of these together, this means that the barber shaves himself if and only if he does not shave himself. This is essentially the statement that P is true if and only if P is not true. We call this a paradox. In general, paradoxes are statements that are self-contradictory, and in general mathematics, paradoxes either, one, show that there's something fundamentally wrong with the objects that you're working with, and that you need to expand or restrict the objects that you're studying so that you can avoid paradoxes, or two, it shows a kind of lack in our intuition. So to give an example of the lack of intuition, there's a thing called Gabriel's horn. So it's an object that has finite volume but infinite surface area. So if you were to paint it, you could fill the cone with paint, but you could never paint all of the walls. So that seems paradoxical because of our intuition about volume and surface area, but it's true. Now, with this Barber paradox in mind, let's examine another version of this paradox, but instead of using barbers, who are cats, we're going to use sets. So now consider the set of all sets that do not contain themselves, and we're going to call this set S. So do notice that the set of all sets would contain this set, right? So this is going to be a subset of the set of all sets. So symbolically, S is simply going to be equal to the set of all X such that X is a set and X does not contain X. Now, similar to the Barber paradox, we can ask a question. Does the set of all sets that do not contain themselves contain itself? So now you can pause the video here and go through both of the cases, if it does contain itself or if it doesn't, and see what happens. It's similar to the Barber's paradox, so you'll get the same result there, but it's good practice to kind of go through this. Otherwise, I am now going to go through it. So the answer is no. This is basically the same paradox on the previous slide. Let's examine them. If S contains S, what does that mean? Well, if S contains S, then it's not a set such that X doesn't contain X. This means that S is not in the set S. So this is a contradiction. Now further, if S doesn't contain S, well, then S is going to be a set such that S doesn't contain S. So by the definition of S, it is a set in S. So again, another contradiction. Thus, this set is paradoxical and it can't exist. So what is the lesson to be learned here? Well, one, sets can do weird things. And two, when building a set using set builder notation, you need to have some restrictions on what you can do. Explicitly in the previous slides, I restricted the elements that I was considering to be in the set or not to be within another set that I've already previously defined. So for this course, you need to explicitly make sure you're always doing that. So kind of another fundamental idea that's happening here, this set is paradoxical precisely because it refers to itself, right? So the set of all sets that do not contain themselves is self-referential when I ask the question, does it contain itself? So other classical examples are the set of all sets that have never been considered. In order to determine whether or not a set is in the set, you have to consider it. So nothing can be in the set, but then that means the set's the null set. So if you consider the set of all sets that has never been considered, well, you've considered the null set, so there's nothing there. So it's paradoxical in the same sense. And these paradoxes have occurred in pulp culture. I'll put a video at the end of this video. And anytime you have an object that is self-referential, you're opening yourself up to these paradoxes due to the existence of these kind of recursive questions that you can ask. Okay, so now just kind of the memes du jour. 2 memes regarding Russell's paradox. And now I will post a video, which hopefully I don't get copyright striked for, but it's just another example of these self-referential statements that lead to paradoxes.
Judas. Jim is my enemy, but it turns out that Jim is also his own worst enemy. And the enemy of my enemy is my friend. So Jim is actually my friend. But because he is his own worst enemy, the enemy of my friend is my enemy. So actually Jim is my enemy. But